Hi and welcome back to the second part of this linear algebra recap lecture. Now it's about normed vector spaces. So normed vector spaces, or the word normed, just basically means that we are measuring the length of vectors now. A normed vector space is a vector space which has a function, which is the norm, which maps a vector to a value which is positive or at least non-negative, and it has to satisfy the following properties. Now the first one, very important, is the triangle inequality. So what it basically says is that I have a vector v, so I go like this, and then I add the vector w, which goes like this. Then this is longer than when I go straight from the starting point here to the end point. I mean, this is important for measuring stuff, right? This property. Then the second one is the homogeneity, and this means that if I scale my vector, then this is the same like scaling the length. And it has to be here the absolute value of alpha, because otherwise we might get negative lengths. So the norm is a length which is mapped always to a positive or non-negative value. So if I have here a vector v and I scale it negatively, which means basically that I would get this vector. I don't know, I multiply this with -2, so I get this vector, and then the length of this vector is not affected by the sign I have. Now the last thing is that if the norm of a vector is zero, then it's the zero vector and vice versa. So only the zero vector has actually a norm of a length of 0, which makes also kind of sense, I guess. Okay, so this is the definition. Let's look at some examples. So what is most common, or what you would probably also know, is already the Euclidean space. The d-dimensional Euclidean space is the space r to the power of d, equipped with the Euclidean norm. And the Euclidean norm is always denoted usually like this, with a small 2 here. But it's like basically the default norm. So sometimes if it should be clear from the context, then usually it's the Euclidean norm, if not said otherwise. Yeah, it's defined like this. So we square just all of the elements of the vector, sum them up, and then make the square root of it. The visualization is like this. So we have here vector v, and the first coordinate is v1, and the second one is v2. And then we square the length of the coordinate v1, and we make the square of v2, and we add this. And then the length of this vector v, which is the norm, the Euclidean norm. Yeah, it's basically what you know from the Pythagorean theorem, at least in the space r square, that the length of the hypothenusis, I'm sorry, I don't know how to pronounce that. So if you have a triangle with a 90 degrees angle here, then the length of the hypothenusis, this is called. The length is the same like when you add the squared v1 and v2. Now an interesting relation of the Euclidean norm is given by the relation to the inner product. So the inner product can also be defined by multiplying the lengths of the vectors and the cosine of the angle between them. This again, like you can derive this if you build here some matrices, some triangles with a 90 degrees angle. So if you build this triangle and then you apply the definition of the cosine, then you will arrive here at this definition. The more similar direction the two vectors have, the higher is the inner product. And also the longer the vectors are, the higher is the inner product. And this is quite relevant for later when we will use, or basically what is very often implicitly assumed, is that the inner product is a similarity major. Similarity just because the vectors are more similar if they point into the same direction. Orthogonal vectors are vectors which have here a 90-degree angle. If two vectors are orthogonal, then the cosine of the vectors is actually equal to 0. And this means then also that the inner product is 0 according to the definition we just had. And yeah, orthogonality in data mining is often also an equivalent formulation for saying that these two vectors or observations do have nothing in common. So for example, if you observe for yourself, okay, I don't know, you like dogs, you don't like cats. Who doesn't like cats? But okay. And you like birds. But then there is some other person which doesn't like dogs but likes cats and doesn't like birds, and you compute the inner product of them, then you see that this is actually 0. So if you say basically this is one vector and this is one vector and you compute the inner product, then this is 0. So this means that these two vectors are orthogonal, and then if you compare what happens, whenever a 0 is chosen, the other person chooses a 1 and vice versa. So they have orthogonal interests. And two vectors are called orthonormal if they are orthogonal and they have unit norm, so they just have a length of 1. Another interesting thing about inner products is its relation to projections. So the inner product of a vector v and a normalized vector w over the norm of w. So this vector is just another way of writing or making sure that this vector actually has a norm of 1, because the norm of w divided by the norm of w. And then the norm of w is just a scalar, so I can just multiply this out basically. I multiply this out of the norm, and it remains this norm of w. So this w is this w. And this norm is this norm. And then we have 1 over the norm of w times the norm of w, which is just 1, right? So a vector which has this form here is always having a norm of 1. So the inner product computes the length of the projection PV of v onto w. So for example, here we have the two vectors w and v, and the vector PV. So this vector computes the projection of v here onto w. So the definition of the cosine of phi, which is here this angle, is equal to the norm of PV divided by the norm of v. So this is basically just a definition of the cosine in a triangle with a 90 degrees angle, which is here. And then we just transform this equation, so we multiply with the norm of v, and then we get that the length of this projection vector PV is actually equal to the cosine of phi times the norm of v. And then we insert the definition of the cosine given by the inner product, and then we arrive at this term here. And then we know the length of PV, and we know that PV is the projection. So it has to be on W. It's a projection onto W, so it has to be on W. So what we do here in the last equation is we multiply with W divided by the norm of W, and then we arrive at our final term. So projections are, for example, important if you want to compute distances between points and a plane or something like that, because actually if we know this measure here, if we know the length of PV, then we can also compute this distance here. This length here is basically the distance of the point V to the plane, which is here given by the vector W. Okay, so now let's have a look at another norm. This is the Manhattan norm. The Manhattan norm is basically defined as this. So we have here again the notation, but here we have a small 1 as an index. But because I don't like this notation so much, so to see in the first place what is actually used, like 2 norm or 1 norm, then here for the 1 norm we need just the 1 torque basically. And what it does is it adds the absolute values of all the coordinate values of my vector. So for example, we have here like the length of this vector here was the norm of V, but the Manhattan norm of V would be this piece added to this piece. So this is here the absolute value of V2, and this is the absolute value of V1, and then you can see, or you can estimate that the 1 norm is in this case, for example, longer than the norm of V, the Euclidean norm. So the Manhattan norm computes the length of a vector coordinate-wise. This is the example here for 2 dimensions. And why is it called Manhattan? Well, it's basically the distance you have to go if you want to go from one point here to the other point in Manhattan, because it has this grid-like structure. So you cannot go straight from one point to the other, but you have to go a bit around, like this. This is then the distance basically you have to walk in Manhattan. And then we can generalize this concept of having one norm and 2 norm and other values p, but only for the values from 1 until infinity, including infinity. So infinity is a special case where the p norm of v is defined like this. So if you insert here 2 or 1, then you see that this will correspond to the Euclidean norm and the Manhattan norm. But we can also add other values. And the 2-dimensional circles, so which are the points which actually have a distance of 1 from the origin, look as follows. So for the Manhattan norm, we get here this diamond shape. And for p equals to 2, we get the normal circle. And for p equal to infinity, which is actually computing the maximum of every coordinate, we get this square. So you see that depending on the norm, a vector can have different lengths. For example, this point here has here a length of 1 in Euclidean norm, but it has a larger norm than 1 in the square norm because it's outside of the circle. So everything inside the circle has a norm of smaller than 1. And if we look at here the maximum norm, then we see that it has a smaller norm than in the Euclidean norm, because it's inside the circle, so it has the norm smaller than 1. Okay, so the norm measures the length of a vector. Can we also measure the length of a matrix now? Yeah, the answer is matrix norms are the same, but different. Yes, we will see this, we will discuss this now in the last part of our lecture. See you then.